You can engineer the most powerful processor on the planet, capable of billions of calculations per second, and it will still stall out if you hand it a set of human instructions. That's because a CPU operates strictly in binary logic. It understands voltage highs and lows. It has no concept of human-readable high-level syntax, like C++ or Java. Between the code we write and the hardware that runs it, there is a total communication vacuum. To bridge that gap, we have to inject a specialized piece of software in the middle, a translator. But looking at the structural map of computer science, you won't find a single universal translator. Instead, the industry relies on three distinct architectures: compilers, interpreters, and assemblers. Each of these three architectures prioritizes a different variable, balancing the time spent translating code against the speed at which that code eventually runs. We start with the compiler. Its defining mechanic is bulk processing. It translates your entire source program all at once, generating a complete standalone file of machine code before a single instruction executes. Like translating a massive English novel into French, you wait for the whole project to finish before distributing. The advantage is execution speed. Because translation is finished, the CPU sprints through raw machine code without pausing to decipher it. You translate the code exactly once, and you can run that executable thousands of times with zero translation delay. But that upfront processing carries a cost. Large programs can take serious time to compile. Worse, if you have 10 syntax errors scattered throughout your code, the compiler won't stop at the first one. It processes the whole batch and lists every error it found at the very end. Compilers sacrifice upfront preparation time to achieve high runtime efficiency. That trade-off makes them the standard for heavy, resource-intensive software written in languages like C or C++. The interpreter translates and executes code strictly one statement at a time. Read line 1, translate, execute. This creates immediate overhead. By forcing a constant loop of translating, then executing, overall runtime is much slower than a compiled equivalent. If the compiler is a book publisher, the interpreter is a live spoken language translator. You say a sentence, and they repeat it in the new language immediately. That immediacy allows the program to start running the second you hit go. And because it works line by line, the program will halt the moment it encounters a problematic line, showing the programmer exactly where the logic failed. Interpreters trade raw runtime speed for immediate execution and localized debugging. That makes them the backbone of fast-to-write scripting languages like Python and JavaScript. There is a third input path to consider: assembly language. When programmers need to bypass high-level syntax entirely, they write in assembly, which acts as a human-readable shorthand for raw hardware commands. To translate this shorthand, we use an assembler. Because the input maps directly to specific machine instructions, it acts less like a complex processing engine and more like a high-speed dictionary lookup. It bypasses the heavy logic trees of a compiler or the looping structure of an interpreter. It simply swaps the short-form text for the exact binary equivalent. When engineers are writing firmware or device drivers and need absolute control over the hardware, the assembler provides that direct bridge to the CPU. This matrix tracks the specific profiles of our three engines. High-level languages require either a compiler for bulk processing and execution speed or an interpreter for line-by-line agility. Assembly language uses an assembler for direct hardware mapping. If you run a 50-line script and the computer translates it line by line as it goes, you are working with an interpreter. If your system digests the entire program before a single operation runs, prioritizing runtime efficiency, that's a compiler. We know what a compiler does to solve the translation problem, but that high-level view hides the engineering happening inside the software itself. A compiler is actually a multi-stage pipeline. Before it can output binary, it has to break human text down into individual tokens through a process called lexical analysis. Tracing the flow of data through these internal stages is where the study of compiler design begins.